we are going to give the essentials of material balance with reaction initially and also without reactions also. We have representative problems. Okay. Uh, and here actually, though you know this process calculation in variety of way, we are going to have some two new methods, not new actually. These are all well explained in this book Felder. Whereas this much explanation is not available in any other book on process calculations. Okay, I'm going to highlight that two methods, namely extent of reaction and atomic balance methods. Okay, by the way of two, three problems initially. And you'll feel that these methods are quite nice for solving any kind of process calculations. Okay, and we will also use this in the subsequent problems, namely this atomic balance and extent of reaction methods. Okay, for that I have three examples. So this entire video is already available, and I'm going to highlight only. So video may be around some 20, even 10 to 15, 20 minutes also. Whereas today I have to finish this whatever that already marked. So we'll be hardly spending about 5 to 10 minutes for a problem. Sometimes 2, 3 minutes also. Okay, to start with, we'll take up this nice problem which were asked in our GATE in the recent year. Okay. Yeah, maybe initial 40 minutes you please allow time for me, and after then we'll allow you to ask any question. Okay. Yeah. To start with, okay, of course, I am not going to explain you the theory or anything. This by the way of solving the problem, you will understand the whole of the process calculations. In that way, only the representative problems are chosen, and but additionally, you are expected to go through all the thing marked. Okay, in the checklist. Okay, please do that. At least if not, if you haven't gone through, at least try to spend time today and tomorrow, and latest by Sunday you finish everything. Okay, that 4 hour of portions are already marked. In that 4 hour of portions, I am taking some representative content, which are all about some 2 hour of content, trying to finish it in 40 minutes time. Okay, to start with, this is about formaldehyde from oxidation of methane, which is involving two reactions. So we have this methane in the methane and oxygen as a reactants. Okay, and we are having this all these contents: formaldehyde, water, CO2, and even there is unconverted methane and oxygen present. So we are given with the data about how much of methane is entering the reactor, and the product gases has all these content. Okay, methane, oxygen, or is all the components are there in the product, which means there is a incomplete what is it conversion, or is there is unconverted product feed reactant available in the product. Okay, the flow rate of this thing. Okay, we are having given with the flow rate of methane, oxygen, CO2 leaving the reactor also given. Methane entering the reactor is given, and how much of these contents, methane, oxygen, and CO2 leaving the reactor are available. So what is asked is to find how much of oxygen that has entered the reactor. So for that, of course, you can use usual calculation service based on the data of your CO2 in the product. You can possibly find how much of CH4 would have been utilized for that reaction, and accordingly you can calculate how much of CH4 has been used. You can use the any other method, but the method what you are going to learn, namely this extent of reaction and atomic balance, will help you to solve the problem in a systematic way. Okay. Okay. So we are having this data. There is 60 mole of methane entering the reactor. Okay, you can nicely put a schematic. What is entering? Methane and oxygen are entering, and the product is having methane, oxygen, formaldehyde, and CO2. All the contents involved in the chemical reactions are there in the product. Okay. Now we have this equation. Actually, this equation you would have come across in your thermodynamics in this reaction equilibria part, which is discussed in our Smith and Vaness book. So what is this Ni? Ni refers to the moles of a component. Okay, in the reaction mixture, that is equal to what is there initially, Ni naught, that is plus summation of that this is actually getting consumed or generated. This nu I refers to the stoichiometric coefficient of a component I, and J, what is that? This is stoichiometric coefficient of a component I in Jth reaction. Okay, that is why nu I J, and multiply that with extent of reaction extent of the corresponding reaction. There are two reactions here. So extent of first reaction or extent of second reaction. So we'll help you to understand this for the component, say this methane. Okay, and for convenience, you write everything in terms of moles. Okay, N1, these things are the moles of these corresponding components. Okay, now we'll write this equation for component methane in the product, which is we taken that as N3, which is equal to N3 is equal to or is N. This is simply N of CH4 in the product, and N of CH4 in the initially. How much of CH4 is there initially? We are given with that data. There is 16 moles are initially available, and how we are getting this? Okay, this is summation of nu I of the J3 reaction multiplied by extent of the J3 reaction. Okay, this nu I is simply the stoichiometric coefficient of the J3, stoichiometric coefficient of component I in the J3 reaction. Okay, we have two reactions. Let us name this as reaction 1 and 2. So what is the stoichiometric coefficient of methane in the first reaction, which is actually simply 1 here, 1, 1, 1, 1. This is 1, 2, 1, 2. Okay, and we'll use this convention. This for the reactants, we'll use this stoichiometric coefficient as negative, and for the products, the term will be simply positive. Okay, so here CH4 being the reactant, and the stoichiometric coefficient of that is -1 for the first reaction. So -1 multiplied by extent of first reaction. Okay, that's why minus E1. Like that, we have to make a summation, right? So this methane is also there in the second reaction as well. Second reaction also it is having a stoichiometric coefficient of -1. Okay, -1. And the extent of that reaction is E2. So I hope you can understand this. Okay. So what is there initially available is 60 mole, and how much of that is getting converted or produced. That's what only we are writing actually in terms of extent. This is nu I of the J3 reaction and nu I of the first reaction and second reaction. All are written like that. Now for I'll explain for everything. Okay. What is for the O2? So O2 is there in the first reaction, which is having a stoichiometric coefficient of -1, and here it is -2. So that's why -1 and 2 -2 E2. Okay. What is there initially available? We are taking it as N2. So N2 is the initial amount, and what is these terms are available here. Okay. By this way, we have written for O2 in the product, like that for formaldehyde in the product. So formaldehyde initially, no formaldehyde is there, only methane is entering along with oxygen is entering. There is no formaldehyde, so always Ni not of formaldehyde is simply 0, and formaldehyde is involved in only in the first reaction, which is having a stoichiometric coefficient of 1. So from that, we are simply writing N. This formaldehyde, moles of formaldehyde in the product is simply extent of first reaction. Of course, extent also has a unit of this N. Okay, moles. Here in this case, moles per second. So it is also in mole per second. Okay, like that for CO2. CO2 is involved in this second reaction alone, which is having a stoichiometric quotient of 1. So that's why it is E2. Like that for water. Water is involved in first and second. Here it is having quotient of 1 and it is 2. So 1 E1 plus 2 E2. So that is what is there in that is what is that for this water. Okay. So by this way, now we have written. Now at last what we are going to solve? We are actually going to solve for N2. Okay. For that only we are doing this systematically. We are writing what is there in the product. Everything is written in terms of E1, E2. Okay, E1, E2. Shall we solve that now? Possibly. So we are having some data. These are the product contents. So this for this feed content we are having this products. So CH4 in product, O2 in product, CO2 in product are available. So this content is directly given. So what you are getting? This E2 is directly solved now. And using that, now we can also solve for E1 because this equation is having except E1, all the others are now known. So now we can also solve for E1. So extent of first and second reactions are solved. Once that is solved, all the product contents are known. Okay. The product contents are now relating this N2. No? N2 is simply O2 in the feed receiver. This N4 is now no, directly given, which is also connecting this E1 and E2. Or is I am simply using extent, or is epsilon instead of epsilon. I am saying like extent. Okay, E. Okay, N2 minus E1 minus 2E2, which is directly available. Okay, and N2 alone is to be solved. So N2 is directly coming, which is 40 mole per second. service. We are simply solving for how much of oxygen entering the reactor. So for that, we are writing the product contents in terms of the extent of a reaction. Okay. And this there are, since there are two reactions, there is going to be extent for the first reaction as well as for the second reaction. Okay, extent is having the units of this n whatever is the constant. The stoichiometric coefficient doesn't have any unit, right? Okay, and of course it is having sign. For the product, it is positive, and negative feed, it is negative. Of course, with the proper stoichiometric coefficient. So this is -2. This is actually +2. Okay, that we have to consider. Hope this is simple, no? Straightforward. Let us also see the other method, which is atomic balance method. In this atomic balance method, we need not write anything about the reactions. Simply, you can make balance on the whatever the atoms entering. So, what are all the atoms here now? Carbon, hydrogen, and oxygen. Only these three are involved. So, you can write the balance for carbon, hydrogen, and oxygen. So, whatever the atoms entering, they should leave. Of course, there is no atom getting generated or consumed. In terms of atom, of course, components are getting formed and consumed, whereas in terms of atom, they are conserved. So in that way, we can easily write balances. So actually, we'll be ending up with three balances: one balance on C, and another on H, and another on O. That's it. They are making the components. So we can simply write three balances, and we can easily solve them. Let us see how this is done. So we have again taken the data. Here, what are all available? These are all already reported, and these are all known. We are again going to solve for N2. Okay. So now let us write the balance on C. So what is how much of C is entering here? In 60 mole per second, that is CH4. There is 60 gram atom of this carbon is available. So it is simply 60 multiplied by 1. That is 1 methane is having 1 C. That's it. No. So 60 into 1 is the gram atom of methane entering. Like that, how much of methane is how much of carbon is leaving? So in N3, which is this methane, 1 N3 we have 1 C. Like that, 1 N5 we have 1 C. And 1 N6 1 N6 we have 1 C. So in that way, we have to write everything. So this is 60 entering, and this is 26 multiplied by 1, and this is 4. This is 4 multiplied by 1, and here this N5 is having 1 C. So by that way, how much of carbon is entering and leaving? So we have the nice balance on carbon. So which is directly giving you the data of N5. What is that? The how much of formaldehyde is leaving. So that you are actually solving directly, but which is not needed, but that will be used for the subsequent equations. Okay, now like that we can make balance on oxygen. So oxygen is entering simply as N2, and one N2 is having 2O. So in that way, N2 into 2. That is O2. O2 is molecule. One O2 is having 2O, 2 atomic oxygen. Okay. So in that way, 2 into N2, that is what is entering. And what is leaving? Oxygen is leaving here, and here, and here, as well as here. Okay. So for all that thing, so how much of O2 is there here? N4 is actually 2. In one N4, we have 2 2O. Okay. Like that, one N5 we have 1O, and one N6 we have 2O, and one N7 we have 1O. So that everything we have to write. So 2 into 2, it is what is that? 2 into 2. Oh, 1 minute. Yeah, balance on O. This is this is 2 multiplied by this is actually in there is 2 moles of N4 is available. So which is 1 N4 is having 2 atoms. So that's why it is 2 into 2. Like that for N5, which is simply 1. So N5 into 1. And here this is N6. N6 is actually already 4 multiplied by 2. Okay. So 4 into 2. And here it is N7. 1 N7 is having 1 O. So N7 into 1. So now we have too many variables. Service N5 is already available. This N2 and N7 will be having as unknowns. Okay. Okay. So far we have now one equation with 2 unknowns. Okay. Of course, already this is solved. Now this is one equation with 2 unknowns. We also have one another balance possible, which is balance on hydrogen. So how much of hydrogen is entering here? In 1 methane, we have 4 hydrogen. Okay. So always 60 multiplied by 4, that is what is entering. There is a atoms of hydrogen, gram atom of hydrogen entering. That is equal to leaving in this methane, which is 26 into 4. Okay, like that. Here it is N5 times 2. Okay, and this is N7 times 2. So by that way, you have to write N5 into 2, N7 into 2. So here directly you are getting this N7 solved. So using this N7, now you can get N2. That's what is the left out. This method, this extent of reaction and atomic balance methods are very straightforward method. Whereas in a usual problem, how you have solved. Of course, usual solution also I have written here. This is available in this process calculations textual course. Okay, so this is your reactions, and we are given with this data. So you have to calculate at last how much of O2 is entering. So based on the data of methane in the there is 4 mole of CO2 in the product indicates. Okay, we have 4 mole of CO2 in the product, which means 4 mole of CH4 would have been utilized by this reaction, and for which 8 mole of O2 is utilized. Okay, from this CO2 we have some information. Then how much of CH4 would have been reacted as per reaction? One is CH4 in the feed minus CH4 in the product. That much only as actually utilized. And out of that CH4 utilized for the reaction 2, how much? Already we have that because of CO2 data. So from that, now how much of CH4 is utilized as per reaction 1 is available. Then how much of O2 got utilized for the reaction 1, and then we can now get to know how much of O2 entering is O2 used in reactions 1 and 2 and O2 in the product. So of course, this method, though appearing to be simple, but you have to start properly. You have to start, you have to get some, you have to easily start with a, you have to start with a nice point. I could say like based on the CO2, I can say about how much of methane is utilized for this reaction, and the balance would have been used for these reactions. So by that way, actually, we have to go in a cyclic or some sort of fashion. Whereas this extent of reaction method or atomic balance method are very straightforward. Without worrying anything about thing, we can systematically write the equations. Say, for example, how many atoms are involved? One, two, three. C, H, and O. So you can simply write three balances, and definitely you'll be getting three equations, and you can solve them, and all the unknowns will be available. Like that. Whereas for the extent of reaction method, here you have to write the chemical reactions and write the product contents in terms of the extent. For this, definitely you have to write the chemical reaction. Whereas this atomic balance method, you don't need to write any reaction. Otherwise, for suppose you don't know the kind of reaction happening, but you know some contents entering and some contents leaving. For that and all, you can easily use this atomic balance method. Okay, we'll maybe any discussion later on this kind of a new method, not new method, actually well explained in our Felder. I would recommend you to go through this book, Felder, Elementary Principles of Chemical Process, which is a fantastic book for this process calculations. Okay, okay, maybe you can you can understand this by another two more examples. So let us not wait further. Let us take up this problem. This is about calculating the excess air in the case of combustion of propane. So we are given with the product contents. So products are CO2, CO, water vapor, nitrogen, oxygen. So which indicates that we are using, okay, there is excess air. Okay, it is already mentioned. Okay, air means O2 and N2 are there in the feed. And because of this CO2 and CO also coming up, so it is a kind of incomplete combustion happening. So always we can, based on this product thing, we can write the reactions possible. Okay, your propane is reacting with, of course, only the oxygen is the reacting component of the air. So propane reacts with oxygen and to give CO2, as well as it is also giving CO. This is complete combustion. This is incomplete combustion. So this is a possible stoichiometry. So for this stoichiometry, now using this stoichiometry to write this product contents in terms of extent. Okay, so we are given with some data, like we are having the data of this product composition. So we can choose the basis. So the basis actually has to be chosen wherever we have a complete specification. So we are choosing the product composition, or we are choosing the base of 100 moles of product. So by that way, we can simply take this as the moles of the product components. Okay, so by that way we have this data, and we are going to relate them in terms of extent. So for that, again, we are taking this simple equation: Ni moles of a component equal to initial moles plus simply summation of nu ij extent of the jth reaction. Okay, so what is nu ij, which are all simply possible from here? Okay, let us now do it for CO2. CO2 is involving in the first reaction alone, and it is not there in the feed initially. Okay, these are all simply product contents, and feed is simply propane, pure propane with excess here. Okay, so CO2 is not initially there, so otherwise Ni naught is 0, and what is there is simply getting produced. This stoichiometric coefficient is 3, and extent is simply extent. Okay, stoichiometric coefficient is simply 3. This extent is extent of first reaction. CO2 is there only in the first reaction alone. Okay, like that. Now for CO, CO is actually given in the product content is product is having 5 moles. Okay, this yeah, CO is actually 3.5 mole in the product, which these contents are available. Okay, what is this? How do you get that? CO is involving in this second reaction, but again ensure that you are writing the balanced stoichiometry. Okay, and 3 is the stoichiometric coefficient, and this is involving in the second reaction 3 into E2. Whereas this is 3 into E1. Because of first reaction, this is second reaction. Like that for water. So water is there in both the reactions. Okay, this is having a stoichiometric coefficient of 4, as well as this also 4. So 4 into E1 plus 4 into E2. Of course, there is no water in the initial. Okay, that is Ni naught is simply 0. Okay, these are all, this is for water. Like that for oxygen. So oxygen is there in the feed as well, and how oxygen is there in the product as well. Okay, how much of oxygen is there in the product? Okay, which is given. So that what is there in the product is already given, and what is there in the feed? This Ni naught is 21% of N2. There is this small N2. I am using it for air. Okay, don't confuse with capital N2. Okay, there is since we are using this same symbol. Okay, this N1, N2. So 0.21 of N2 is your O2 initially present, and how much of O2 have been utilized in the reactions with these terms. So for that first reaction, this is minus 5 into extent of first reaction, and this one, this is minus 3.5 into extent of the second reaction, or is this minus coming because of reactants. So these are all this oxygen is a reactant. And N2 simply what is available in the feed is going to come out. How much of that is available? There is 79% of this N2. Okay, so that way we are writing this N3 content, N2 content is also already available. Like that for this is there is no propane in the product, which indicates completely burnt. Okay, so always C3H8 is simply 0, but in terms of extent it is actually. So what is N1 available? Initially available is N1. Ni naught is simply N1, and extent of first reaction, or is extent minus extent of first reaction minus extent of second reaction, because it is getting consumed as per reaction 1 and as per reaction 2 with a stoichiometric coefficient of 1 1. Okay, so by this way now the product contents are available in terms of extent. So already we have this data, so you can easily solve for E1, E2, because this CO2 content, CO content are available, so you can directly solve for E1 and E2. Okay, then what is actually needed? We are supposed to calculate the excess air. So for that we need to find how much of air is actually entering and how much of air is actually theoretically needed. So that calculation also we are supposed to make. Okay, from the data of N2 in the flue gas, also you can solve for N2, actually how much of air entering. Okay, okay, this is this equation. From that you can solve for directly how much of yeah, air is entering. Okay, now how much of air is actually needed? That is stoichiometric requirement. For that we have to work on. So okay, from the data of CO2 in the flue gas. Okay, always these are all already done. Okay, always how much of N1 is entering? Always how much of feed, actually how much of your fuel, that is propane, is entering? That also we need, because for that only you are going to calculate how much of theoretical air required. So this you can solve, because here we have this data now. This is the equation connecting this N1 and the extent. Already we have this extent 1 and 2, and from that N1 we are solving. So once the N1 is available, now you can calculate how much of what is the stoichiometric requirement of O2 for this reaction. So O2 stoichiometry, how much is the stoichiometric requirement? So stoichiometric requirement is always based on the complete combustion of the reacting component, which is actually the in the combustion reactions. Always this stoichiometric requirement is based on based on the complete combustion. So complete combustion means carbon has to convert it into carbon dioxide, hydrogen to turn into water vapor. Okay, so that is a complete combustion. So in the case of sulfur available, it should go to sulfur dioxide. And what else? Maybe if nitrogen is also taking part in the reaction, it will be turning to NO2. Of course, normally this nitrogen is considered to be inert. Okay, okay. Rest the components like C turning to CO2, and S turning to SO2, H turning to H2O. Okay, so these are all the complete combustion reactions. So based on that only you are supposed to calculate the theoretical air required. Okay, so now we are calculating the O2 stoichiometric requirement. This is this much of propane is entering. For one propane, we need 5 oxygen. Okay, from that we calculated how much moles of O2 is required, and what is the excess percentage excess. How to calculate? So what is entering minus what is actually what is the stoichiometry? Say what is actually entering? What is actually entering is 21 percentage of this content. Okay, which is with this 0.21 into n2. This n2 already we solved, and from that we have this. Okay, that we have this is a O2 actually entering. Minus what is actually needed, what is called as a theoretical requirement. So this is actual minus theoretical by theoretical. So from that you can easily say what is the excess O2. Of course, you can also verify that excess O2 and excess air are the same percentage. Okay, because again in proportion it will be the oxygen will be N2 will be entering and leaving. Okay, so this percentage excess O2 and percentage excess what is it air also the same. That is left to you for verification. Okay, so here again to simply say how did you solve that based on this extent of reaction method we are solving. So we are given with this data, we are writing them in terms of extent, so that this extent 1 and 2 are now directly available. Using that we are getting this n1 value. Once the n1 is available, and n2 also we already solved based on this thing, which means how much of this propane is entering and how much of air is entering is known. What is needed is we need to calculate how much of air is actually theoretically needed. So for that, theoretical requirement is simply based on this complete combustion reaction. So for 1 mole, we need only 5 mole. So for how much N1, how much of O2 is needed, accordingly you calculate. Then you report in terms of percentage excess O2. Percentage excess O2 and percentage excess air are the same. Okay. So what is asked is percentage excess air. Okay, fine. Yeah, the same problem we'll also solve by atomic balance method. Okay, for atomic balance, you need not write anything these reactions. We are simply going to write what is there in terms of components. Okay, these components are there. We have this complete data, and N1, N2 we are actually going to solve. So what are all possible now? So simply first we can write the balance on this nitrogen. What is nitrogen leaving is what is nitrogen here. Of course, you can need not write in terms of atom balance. Say, always atom balance is simply writing in terms of N. You can also write balance in terms of the molecular nitrogen also. Of course, at last we are going to ensure that the same component is considered. Okay, balance on N2. Of course, N2 here is also a kind of non-reacting. Of course, you need not worry about this anything in the about the reactions in this atom balance method. Okay, whatever the N2 here is N2 here. Okay, so N2 balance on N2 is 0.79 into N2, 0.79 into N2. Okay, that is equal to 73.1. This is already available. So based on that N2, there is nothing but the air amount is automatically solved. Always this is now readily available. We need to calculate this N1. So for that, you can write the balance on carbon or hydrogen. Okay, so let us write the balance on carbon. So how much of carbon is there in the N1? One N1 is having 3C. Okay, so 3 into N1, that is carbon entering, and carbon is leaving here as well as here. Okay, so 5 into 1 and 3.5 into 1. So that is a carbon leaving. Okay, this is 3.5 into 1 and 5 into 1. So that way we have this N1 now solved. Okay, now N1, N2 are available. Or is, what is propane entering? How much of air entering are available? You can now calculate the theoretical O2 requirement. So O2 for 1 mole we need 5 mole, and for this much mole how much of that is required? And from that you can solve for this. Okay. So otherwise, simply this atom balance method, you need not write anything, any equations. Simply you can solve. This is quite easier. Suppose only 2, 3 atoms are involved. Okay. Of course, 1, 2, 3, 4 atoms are there. So you can write 4 balances, but not required here because already this air amount you can directly get, and only one balance alone is enough to solve for this. So with that, we could quickly solve. In comparison to this extent of reaction method, this atomic balance method is quite easier here. Of course, if you want to try a solve by your own way, that things are explained, but the problem is always that method is called as a molecular balance method. So that method is having always a difficulty, always where to start. You have to start properly, then only you will be solving. Otherwise, it will take more. It will take more time. Whereas these two methods are very systematic, and you can definitely lead to the solution, though it is taking some little extra time. Okay, like that. One more problem also there. I suppose we are having. I think I can spend time, or I think the similar approach you can use. Maybe I will skip this part alone. Okay, there, so that I will take up go to the other problems. Okay, so this problem, which is H by C of what is called as a hydrogen by carbon content of the fuel from the Orsat analysis. To simply say, like, Orsat analysis refers to the analysis of the flue gas excluding water. Water content would not have been included in this analysis, but of course water is going to be there in the product. Okay, without by excluding, you'll consider this alone as a dry flue gas, and from that you can solve. Maybe you can go through this. It will help you to solve the problem. Okay. Anything? Any of you want to ask anything? Okay. Maybe if I spend time, it will take some more time. That's what I'm looking. Okay. So, always it is left you as an exercise. Maybe in the next class, if you could not follow this, I will discuss in the coming class. Okay, I'll take up some more nice questions. So this is about simply a nice problem, which is actually 2 mark long back. So this is about calculating the recycle for the given conversion. Now there are two terminology, what is called as single pass conversion and overall conversion. So single pass conversion refers to conversion around the reactor, or is conversion in the reactor. What is entering and what is leaving. That alone is considered, and overall conversion is this overall boundary. Okay, so in this case we are asked to find for the given data of single pass conversion, we are asked to find the rate of recycle. Okay, so for that, what could be done? Okay, so what is the reaction is A giving rise to B, and it is given that 100 mole of A is entering, and how much of product is going to leave, that also needed, then only to calculate this thing. Okay, or is overall boundary if we make, this A is entering and B is leaving, and the stoichiometry is A giving rise to B. That means 100 moles of A entering means 100 moles of B also will leave, definitely, because no other A leaving. So otherwise it is simply the overall conversion is simply 100%. Okay, there is a simple data you can easily say, because the overall boundary says, so whatever is entering, it is leaving. Of course, it is A is turning to B. Otherwise no A is leaving out, which means all the A has been consumed, and it is turning to simply product. So whatever the 100 moles entering, it is leaving us 100 mole of B, because of stoichiometry is 1 giving rise to 1. Okay, that is one thing, but what is needed is we have to find this recycle amount. So the process is actually, reaction is happening, the product pure P is leaving, and unconverted A is recycled back. So the single pass conversion is given, and based on that, how much of thing is recycling. The single pass conversion is 20%, and we need to find how much of this product is reactant is recycled. What is the amount of R that we have to calculate. So for that, you can say denote this M and E. Okay, so this conversion in the reactor, there is a single pass conversion is given as 20%. So what is the meaning of that conversion? How much of reactant is entering here and how much of reactant is leaving. That means how much of reactant is consumed. Okay, this is the amount of A getting consumed in the reactor divided by amount of A entering. So amount of A consumed divided by amount of A entering, there is a meaning of conversion. Okay, this is a fractional conversion is given. So A in M minus A in E divided by A in M. So that is what is a conversion definition. So we can again rearrange, and you are having this A in M and alone otherwise this is A in M, and this is 0.2 into A in M. So you can this is 1 minus 0.2, you will be having 0.8. So that is equal to A in E. Okay, what is A in M? That we can also say in terms of this and this. Okay, so for that, A in M is A as fresh, and A in E in yeah, actually whatever A in M, that is equal to A as fresh. So what is here is A as fresh multiplied by what is A in E itself. Of course, this all the A in E is coming back. That's why you are supposed to write that as A in R. A in R is nothing but A in E itself, because whatever the E entering, it is leaving as product, and which is pure B, and A is simply all the A of this E is going here. Okay, so by that way, this A in M, that is A in M, is simply A in here and A in here itself. Whatever the A here is simply coming here. Okay, by that way, we are now having this another equation, which is already we have this one equation. This is another equation. So using these two, you can actually solve for how much of A is here, and from that how much of R is leaving. Okay. Uh, the understanding required is what is a single pass conversion and overall conversion. So how to interpret that? So that way, single pass conversion means conversion around the reactor, and overall conversion is this thing. So overall conversion, you can simply say like 100%, because of 100 mole is entering and 100 mole is otherwise all the things are going to come out. Because since there is no A coming out, you can say like all the A has been utilized and it is turning to simply product B. So by that way, we have this uh, data like how much of B is exiting and how much of, please go through this part. Okay, whatever the essential I highlighted. We'll spend time for this kind of problem, which is involving reaction with recycle and purge. This recycle purge, always purge is quite common whenever you have some inert content in the reaction. Always say in the feed we have this N2 is actually inert here. So always the reaction is it is a production of methanol from this hydrogen and carbon monoxide. Okay, the carbon monoxide and hydrogen is the reacting contents. This nitrogen is also there because of the feed is having some such material. Okay, because of these pressions. And also we have this not everything is converted in a single pass, so there is some we have to separate, and whenever there is separation there is a recycle happening. So this recycle, if you don't have this purge stream, what will happen? So whatever the N2 here, it will be keep on accumulating, and if there is no provision for N2 leaving, then this N2 content will build up and it will lead to demanding more volume. So otherwise, whatever the N2 entering, whatever the inert entering here, there should be a provision to leave in this overall. So of course, there is no N2 leaving here in this product. So it should be left in the purge stream. Okay. Okay. Coming here. So what I asked is we need to find, we are given with this feed for a feed of 1 mole. Okay. And there is also information about how much of recycle is there. Recycle amount is also given. There is a data. And additionally, we are given with some data about this, how much of N2 is there in this mixed feed. Okay. This is mixed feed. In that, how much of N2 is there. So using that, we need to find how much of purge is there and how much of product could be formed. Okay. There is a overall data thing. So we are having this feed composition. Okay. And we need to find this and this. Okay. There is a overall expectation. Additionally, this data, recycle amount, and N2 in M. There is how much of nitrogen is there in this point that is available. So using that, we need to find so many data like calculating this and single pass conversion and overall conversion. Okay. For that, let us see how this is done. Here, we can make a overall boundary. Okay. By constructing overall boundary, the problem appears to be simple. Okay, you need not worry about recycle separation. Simply, what is entering, and in terms of atom, you can easily say like how much of C entering should leave here, and H entering should leave here. So in terms of simple atom balance, if you make, that will help you to solve for this B as well as P. Okay, whereas I'm also using other methods. Okay, or is for a problem there are variety of methods possible. Okay, it is not the whatever the method I'm using is the only method possible. Okay, now let us see how this is solved. We are given with the N2 content here. So for that, so what is N2 here is based on what is N2 here and what is N2 here. Okay, there is N2 at the mixed feed, that is equal to N2 of the fresh feed plus N2 of the recycled feed. Okay, this point is simply these two. That's it. No, so for that I can make a balance. So N2 in M equal to N2 in F and N2 R. Okay, this data N2 in M is 13% or is 0.13 of M, that is equal to, here it is 0.04. Whenever there is a complete specification, choose that as the basis. Otherwise, if there is no mention about F equal to 1 mole, you can also choose that as a 1 mole and with reference to that you can work on. Okay, you are given with a specification like feed is this much percentage, and whenever you have a complete specification you choose that as the basis, which means you can fix this F as 1 mole, and these are all the data in terms, originally it is given in percentage, now you can simply report in terms of mole. So by that we can simply solve everything in terms of mole, instead of solving in terms of percentage. The percentage is applicable only to that composition, whereas by choosing this basis of 1 mole, you have this in terms of mole. Okay, now we have this N2, or is what we need is we need to get the combustion here and here, because we have this content N2COH2, whereas this is a pure content. Methanol product is a pure. This composition, if it is available, that will help us a lot. So for that, first we are trying to find the combustion. There is nothing but X, which is fraction of N2 in this recycle, as well as that in this Purge steam. Of course, whatever the leaving separator is simply as steam is going here, and another is, otherwise it is simply a splitter. Okay, the combustion wise here and here are the same. Okay, so for that, otherwise we are going to find the combustion of N2 here, there is fraction of N2 here, that is also the same here. Okay, so for that this data is available, because using this combustion of N2 at this point, I can say about the combustion here, because we know this data. So N2 in M is from that X is solved. Okay, now we can also make a overall balance. Okay, one combustion is available. So what is the fraction of N2 here is available. Now we can make a overall balance. So overall balance for N2 again. Why it is? Because uh, this whatever the N2 entering should leave in the purge, because it is not leaving here, and doesn't happen. No change happens. This simply in terms of atom balance also, you can say like how much of N2 entering is simply leaving. So by that way, so N2 of feed, that is equal to N2 of the purge, which is I'm noting is B for the purge. Okay, P for the actually purge. Okay, no problem. So this is we are getting a purge amount we are now getting. So how do we say, like already this is combustion is available, or is this X is salt, X multiplied by we are making a balance of N2 of feed, that is equal to N2 of this purge. N2 of feed is already simply 0.04 mole, and purge is B into X, X is simply the fraction of N2. So N2 of the purge is simply B into X. Okay, X is already solved from the balance here itself. Okay, or is balance here. Okay, so using that, X is already available, and now B is available, which means the purge amount is or is this point is available. Okay, I think that is also asked amount of purge per mole of fresh feed, that is now solved. Okay, now this amount, this point we have to solve. So for that, we can now make atom balance. So whenever you have kind of many reactions happening, of course it is synthesis of formation of methanol. So here you can simply make a atom balance. How much of C entering here is to leave here, as well as here. Okay, so by that way you can make a balance on atom balance. So balance on C as well as balance on H you can make, because this C and H are there here, and as well as here, as well as also you can write balance on O as well. Okay, whatever the balance is possible, C, H, O, and as well as N also possible. N is already available, because here readily available. So C and H balance you can make. By that way, we have additional equations. So using them, actually, you can. These equations are lengthy. There is many equations you are getting. Simply, you can solve them easily. So once that are solved, then we have this combustion also solved. Yeah, the rest of the part you can go through. Now, what is asked is a conversion of CO in the reactor. So CO in conversion, what is the conversion of CO in the reactor? There is single pass conversion is how much of CO entering minus CO leaving. That is actually it is asked based on conversion of CO. So how much of CO entering here and how much of CO leaving. So the difference is the conversion amount of CO converted, that divided by how much of CO entering. So this is the percentage conversion is how much amount of CO converted and amount of CO entering. So by that we can solve, like that for the overall process also you can solve. Okay, maybe how much time left? Yeah, I think maybe this part we'll skip now. Or this is slightly lengthy. Maybe I'll you try to solve this problem, or is go through this problem, or is we'll take up this problem alone in the coming class. Okay, now I'm giving time for you people to ask any questions based on these topics. Okay, let me check who are all available. Okay. Yeah, over to you people based on the topics we discussed. Simply, we try to highlight these two methods, namely extent of reaction method and atomic balance method for solving things with material balance with reactions. We also try to solve this problem with conversion or a single pass and overall conversion. Okay, these are all the overall thing covered. And additionally, we also learned about what is excess air and how to calculate that, or what is theoretical air. So that things also covered. Okay. The other two simple questions available, maybe that you can go through yourself. I need not elaborate. So I'm giving time for you people to ask any questions based on these topics. Maybe am I going a little faster? No, I think words are coming very fastly. I think since you have the material readily, I think you can easily follow. Over to you people. Please ask questions. I think. Yeah, Neelakandan sir, I think you are available, right? Thanks. He's from. Yeah, we also have faculty attending these classes. And maybe Roshan was okay, right? My own student of SSN, and he's also now attending these regular classes.
Yes, sir.
Okay, okay. Maybe there are new students. If they are asking questions, it will be better. Okay. In that way, how many are available? Yeah, Mohan Chandra Prasad. Again, I can ask. He is our own SSN student. But to that batch, I didn't taken any classes. Arpuda Selvi, maybe I'm allowing you to
Yes, sir.
ask any question because you people were insisting on this kind of giving time for
Sir,
asking.
the last problem that you were discussing is only solved by it can only solved by using atomic balance.
This one, this
The
recycle problem.
methanol production. Yeah, this
Yeah.
one.
I think you can also use any other method. Say atomic balance alone is not enough, or is not needed. We can also solve by reaction or simply without knowing this method like molecular balance. So, otherwise, you can solve by any other method also. Since we
Okay, sir.
learned
But
that.
I
Uh, uh,
tried, and
uh, uh,
it will be easy when we approach the sum
Correct.
using atomic
Yeah,
balance.
yeah. So since we are we understood that method and we feel that method is kind of very convenient. Whereas the other methods, namely the service usual molecular balance, will take time. Service where to start and how to write. Whereas atom balance, once you know that
Yes, sir.
method, very straightforward. Correct. Thanks. Thanks for this understanding. I think as you also try to solve by the other methods. Yeah. So whenever you see problem, you also try to solve yourself. That will give you more confidence than simply going through these contents. But okay, since the time is limited, time is available, we have to simply follow something also. Yeah. We have student.
Sir, can you go to the second last question?
This one. Which one?
Not this.
Yeah. This one. This is the first one. Or excess air in combustion. Okay.
No,
Whatever is.
no.
Hmm.
Uh, this.
Maybe you can ask by the title. So you can simply go to
Yeah,
the.
this question is
Okay.
recycle for the given
Yeah. Yeah.
condition.
Correct. Correct. Correct.
Sir,
Mm-hmm.
like in your feed is like 100 mole per hour,
Mm-hmm.
but when the recycle is coming like 400
Mm-hmm.
ml
Yeah, we are asking. We are asked to calculate this. Actually, it is already marked correct, but it
mole
is.
per hour. So
Yeah,
how
yeah.
come recycle will be more than the feed we are entering?
Yeah, yeah.
Like
That's what is
this.
no. That is what is actually. Say feed is entering, but so this recycle will be more. Say why it is because we'll be having a combined feed will be more, right? So here, so to the reactor, see, all the feed is A is going to convert it into product. Okay, fine. That is a overall thing. So here 100 moles is tend to at last 100 moles of B will be having, but the conversion is only 20%, which means you need to have 500 moles of A here, correct? Then only you will be having 500 into zero point 0.2. There is 100 moles you'll be getting, right? So at this point you are supposed to have 500 moles of A, correct?
Okay.
Recycle is, the advantage with recycle is you are having a good conversion, overall conversion. But another drawback with recycle is actually your reactor size has to be very bigger. So instead of handling 100 moles, the reactor is now supposed to process 500 moles. Correct? So that is a drawback with this recycle. So drawback, of course, conversion is overall conversion is improved, but the reactor sizes and you need to have a separator sizes, all things to be bigger. So there is a drawback with the recycle. Okay, recycle, of course, we cannot waste the reactant. So in that way also you have to recycle that. Since you are handling more amount of content, for 100 moles, here we need to have 500 moles of A available. That we are calculating, of course. So only then out of that 500 mole, 20% is utilized for these reactions, and balance 400 will be recycled.
Oh, okay.
Of course, recycle, there will be more amount. Okay, this your question is okay. Appearing see, in comparison to this would be lesser, but recycle will be always more. Okay, okay. Any other questions? Because we have time left. Another about 10 minutes also totally available maximum, because we started 2 minutes.
Sir, sir, in this question, will we get product 100 mole per hour?
Yeah. Because say what is entering here? A is entering, and reaction is simply A giving rise to B. Okay, and since there is no A leaving, that means all the A has been consumed. Correct, in this overall boundary. Correct.
Yes, sir.
So in that case, all the A has to be turned into product. So product is 100%. 100 moles of A, 100 moles of B is leaving.
Okay, per hour.
Yeah, correct.
Okay.
Sometimes we'll choose like per hour as a basis. Service because already mole is there, and per hour only everything is. Okay. Maybe this the FastTrack class people, namely Sanmuga Priya, or say these people, if you are asking, maybe your questions also good, because this general class people, if they are asking question, at least the same kind of question the others may also have. So in that way, I encourage you people to ask questions. So it will also help everyone available here. Okay. Okay, today we have taken little extra contents, and also we try to elaborate a method, namely this elaborate these two methods, namely this extent of reaction and atomic balance methods. Okay, these two methods normally, okay, there's these two methods I haven't even explained in my book as well. Okay, this recently I learned, and of course this is very well available in this book Felder. Okay, this Felder book, maybe if you want you can take up that. It's also available in the course Open CH. Okay, there is a course Open CH which is also listed as your enrolled courses. So in that I have given my book collections as text. There is nice book collections in that way. There is a link available. So click on that, and in that there will be a Felder available. Felder third edition is available. Even the solution manual is also available as for that book. In that way, please try to spend time for going through these two methods. So these two methods are effectively used in all of these course contents. Okay. But okay, if you are comfortable with your regular approach, that also okay. But the problem with that is sometimes the method will be differing. Otherwise, suppose you would have taken this as the starting point, whereas the other may take any other point. So otherwise, there won't be any unique way of solving. Whereas this extent of reaction and atomic balance method, every book will be having the same kind of equations: atomic balance on C and balance on O. So by that way, you'll see that these things are common.
Sir,
Yeah, Sarmadi, please, ma'am.
yes, sir. Sir, so far we are solving for steady state, no, sir.
Yeah. Every
Yes, sir.
problem
Sir,
actually we are solving for steady state only.
Yes, sir. Can we get for unsteady state also? For
Yes.
example, for the last problem, sir,
Yes,
before
unsteady.
the recycle, yes, sir.
Unsteady problem also we can use these methods.
No,
Yeah.
sir. Can we use the same method like recycle before getting into the recycle part? There will be a condition called unsteady condition, no, sir.
Yeah, correct.
So can we solve at that particular moment?
Correct.
Inge recycle வரதுக்கு முன்னாடியே the fresh feed.
Yeah, correct. Yeah. You say like before introduction of this mixed content, or there will be only we are solving for steady.
Yes, sir.
Okay, no need to complex with that unsteady part, or
Unsteady,
how
okay,
to bring that to stable thing, that are different topic. Or how to bring that to stable thing is part of our process control course. But again, that will take time. So we can solve them, but let us now concentrate only on the steady thing.
Okay, sir. That is my doubt. Whether they will ask for unsteady state condition
Unsteady
also. If they are
based
asking
problems,
like that.
no. Only everything is based on steady. Okay. So this in our process calculations, and of course in most of our course contents, we are simply solving steady problems. Okay. Only in this control we are taking this the model development alone, and later also it's kind of a steady. Okay, service, simply we are
Yes.
working for steady state. Thank you.
Last problem also, sir. Yes, sir.
Yeah,
For the last problem, sir,
mm,
actually, some component is keep
mm.
accumulating.
Yeah, say,
Should we
okay.
consider the
No, everything is steady. Whatever is entering N2 has to leave.
But if it starts to accumulate, then it will be like unsteady, no, sir.
Yeah,
Unsteady
we
state,
don't
no,
allow
sir.
that condition. So say it is simply whatever is entering has to leave. So nitrogen entering is nitrogen leaving.
Okay,
And
sir.
hydrogen entering, hydrogen leaving. So in terms of atoms, if you say like all the C entering has to leave in this. So atom balance.
Okay, no need to concentrate on the unsteady state condition, no,
Yeah,
sir.
unsteady we don't have. Yeah, always we don't say unsteady is a
Okay,
actual
sir.
condition, but for our gate or this usual problem solving, we take up the problem of steady state. So only for the steady state calculations are easier. Otherwise, you have to it will conditions will keep on change, and for that will be like another differential equation will come up, and you cannot solve them in the available time. Okay, for
Yes,
that
sir.
we
Yes,
are
sir.
having this course
Thank you, sir.
process control separately to understand about that dynamics. Okay. No need to worry now at this level.
Okay, sir.
Yeah, right. Okay, any questions from you people, new people? Okay, if you find this to be difficult, please, you have 2 more days time. And okay, for every at the end of every day, okay, of course, this recording will be processed, and the next day you will be seeing the recording. At least latest by 10 o'clock in the morning, you can see the recording available. Even I will also put a timestamp so that you can go to that concerned problem and ask and try to watch that part alone. Maybe this orientation session, I have put up that video, and along with that, even that what is it, timestamp also available. So this is a new feature I learned, and this will be effectively utilized in the coming classes, coming videos. Yeah, if you maybe this our new batch people, if you find this to be little difficult, you please say your concern, or maybe wait for 1 more day, and at that day also, if you feel any discomfort, please let me know. Okay, at least something to be corrected also. That will be done in the week time, in a week time. Okay, over to students of Shanmuga Priya and Vaishnavi Reddy. Were you able to follow the contents? Okay, at least I know these people.
Yes, sir.
Who is responding? Shanmuga Priya.
Yes, sir.
Shanmuga Priya, right. Thanks. Yeah, right. Yeah, you can again log in with computer as well as you can also use mobile, so that 2 devices you can use, so that at least one thing you can follow, and another thing. So by that way you are allowed to use. Even I have now enabled accessing from 2 devices as well. Yeah, the things are done, I suppose. Okay, and those who missed the classes, you can see the video by tomorrow, latest by tomorrow morning, 10 o'clock. And we'll meet on this coming Monday with actually I'm trying to give contents from energy balance, so that we'll spend time for energy balance. And the last class, that is on Wednesday, we'll cover up the less topics, namely this humidification, the evaporation, and this even whatever is pending, so that we'll try to take up. And always please be available on when a Monday class, which is very crucial part. Normally this energy balance part will feel difficult, so that I will try to help you to understand fastly. Yeah, thank you all for your presence, and thanks to our general batch students. Okay, that will there is because their questions will help the audience, other audience.